Okay, 3.2, number 35. And we got three little functions to make up this piecewise function. All three of these functions, so it's equal to x plus 1 squared when x is less than or equal to 0, 2x plus 1 when x is between 0 and 3, not inclusive, and then 4 minus x, the quantity squared when x is greater than or equal to 3. So basically, if you note this, you know that y equals x plus 1 squared, that's a continuous function. 2x plus 1, that's a straight line, that's a continuous function. Here's another parabola, a continuous function. So all three of these functions are continuous over their domains, which are all real numbers in this case. So the only place we have to worry about, because we want to find out where it's differentiable, are the junction points, all right, at 0 and at 3. So we just have to check those 2 points. Now, we always check for continuity because remember, one of the 4 ways a function is not differentiable would be a discontinuity. So we always want to check because these graphs may not line up, all right? In other words, one endpoint could be here and one endpoint could be there and they wouldn't line up. If the endpoints were lined up or touched like this, then we have a continuous function. Then that's not saying, we're not saying that it's differentiable. We're just saying that it's not going to be non-differentiable because of discontinuity. It could be not differentiable because of something else. It could be a corner, all right? But if it's like this, definitely we got some kind of discontinuity, and then we don't have to worry about checking the left or right-hand limits. If it's discontinuous, it's not differentiable. So let me check for continuity. Now, what was the definition for a continuous function again? You need to remember this. Remember, f of x is continuous at a point x equals c if the limit as x approaches c of f of x exists and it's equal to f of c. So the limit's got to exist and it's got to be equal to f of c. Or at that point. Then we know there's no little holes there or gaps. So let's take a look at these functions. So if I want to check for, first of all, I'll check at x equals 0. Then later I'll check at x equals 3. If I check at x equals 0, I have to take the limit of g of x as x approaches 0 from the left. Then it's less than 0, so I'm going to use this function, x squared plus 1, or x plus 1 squared, pardon me, x plus 1 squared. So 0 plus 1 squared is just 1 squared, which is 1. Now as I check the limit from the right, greater than or equal to 0, that would be over here because x, it's greater than 0. X is, just look at this part here, x is greater than 0. So I use the 2x plus 1 function, which would be 2 times 0 plus 1, which is 1. So therefore, you can see that the limit exists. In other words, the left limit equals the right limit, so the limit exists. Now, is g of 0 equal to that limit? Well, that limit is 1. If I put 0 in here, g of 0 is using this function again. So if I use this function, I also get, because that's where it's equal to 0, 0. So that's g of 0, which is 0 plus 1 squared, which is just 1, so that's also 1. So g of 0 is 1, and the limit as g approaches 0 is 1. So since the limit equals the value of the function, it's continuous. So I can't count that out. So I can't cross out and say, well, it's not continuous. So therefore, it's not differentiable. I can't say that because it's continuous. So now I got to check the left and the right-hand derivatives and see. So it's continuous there. So let's check the derivatives. And again, I'm just going to be using these top two functions because I'm going around 0. Then we'll get to the other functions when we check the other juncture point. Okay, so the left-hand derivative. Again, I have my formula for my derivative at a point. And my point in this case is going to be 0, so I put 0 in for a. And again, since this is negative, as h approaches 0 from the negative direction, I'm going to be taking a little bit away from 0 or adding a negative to 0, which makes it to the left of 0. And I'm using this function here. X plus 1 squared, so that's going to be 0 plus 1. I'm sorry, x plus 1 squared. So x is going to be now 0 plus h, because I'm taking the value there, f of x plus h, or a plus h, pardon me. So that's going to be 0 plus h. That's like my a plus 1 squared. Okay? So this is like your x. X plus 1 squared, 0 plus h1 squared, because we're taking f of 0 plus h. Okay? And then if a 0, when it's 0, it's going to be 2 times, it's going to, well, when it's 0, it's also going to be the same thing, right? So it's going to be the same function because it's also less than or equal to 0. So it's going to be 0 plus 1 squared. So again, we're using this function, x plus 1 squared. X plus 1 squared, x plus 1 squared. Then we remove this. 0 plus h is just h, so I got h plus 1 squared, and then minus, and then I just have 1 squared, which is 1. Then I could square this by using, oops, that's all over, pardon me, forgot that, that's all over h. There you go, it's all over h. And then what I'll do is I'll just multiply this out, so I use my binomial square formula, so that's h squared plus 2h plus 1 minus 1 over h. Plus 1 minus 1 is 0, so that goes away, so I've got this h squared plus 2h over h, and I factor out an h, the h is canceled, I got h plus 2, substitute, 0 plus 2 equals 2. Okay, so that's my left-hand limit. I got to check and find my right-hand limit. Got to move it here, don't want to run out of time. So my right-hand limit is going to be, again, f of a plus h minus f of a over h. Now in this case, h is going to be approaching 0 from the positive direction. So I'm going to add a little bit to 0, so it's going to be greater than 0. So I'm going to use the greater than 0, which is the 2x plus 1. And this again will be the x plus 1 squared function, because that's at 0. So this is the 2x plus 1, and this is the x plus 1 squared, because that's at 0, and this is greater than 0. And if I multiply this out, I get 0 plus h is just h, so I got 2h plus 1. And this is just negative, and then 0 plus 1 squared is 1 over h. But what do the 1's do? They cancel, so now I've got 2h over h. But h over h is 1, so I've got 2. So since we know g of x is continuous at x equals 0, and both one-sided derivatives are equal at x equals 0, then g of x is differentiable at x equals 0. So far we got all the points. We just need to check one more point 3. So let's check 3. And we'll check for continuity first, because if it's discontinuous, then we're done. Well, let's take the limit as x approaches 3 from the negative direction of g of x. Well, that's going to be this function here. Well, that's the less than. I'm sorry. Do I reverse these? Oh no, I'm at 3, excuse me. Yeah, I thought I was at 0. Yeah, so this is to the left of 0. This is between, if you look at your function, okay, this is going to be 2x plus 1 when x is less than 3, and then it's going to be 4 minus x squared when x is greater than 3. So I'll check both these values. So if we look over here, it's going to be this function when x is approaching 3 from the left, 2x plus 1. And if I put 3 in here, I get 2 times 3 plus 1 is 7. But as it approaches 3 from the right, I'm using this other function, 4 minus x squared, and 4 minus 3 squared is 1 squared, which is 1. So the left limit doesn't equal the right limit, so the limit there doesn't exist, so I don't have to worry about what the function is there, it's just not continuous. So since the limit does not exist, g of x is not continuous, and therefore g of x is not differentiable at x equals 3. Remember, if it's not continuous, it's not differentiable. If it's differentiable, it's continuous. If it's not continuous, it's not differentiable. That's the contrapositive. Okay, so that means it's differentiable for all real numbers except for 3. We're okay at 0, but not at 3. All right? So I hope that makes sense. And good luck. And remember, if you have any questions about these after even I go over with them on the videos, then please ask in class, all right?